Hello everyone. In this video, we're going to talk about polar coordinates, which will be an alternative to the Cartesian coordinates that we use currently. So first, let's recall how Cartesian coordinates work. Say we're given a point in Cartesian coordinates, which we usually denote x, y. What does this mean? Well, I like to think about coordinates as directions to get to a specific point. So the directions we might give are start at the origin, walk east or west x units, depending on whether x is positive or negative, and then walk north or south y units. And this is how you get to a point specified in Cartesian coordinates. Polar coordinates work a little bit differently. If we're given a point in polar coordinates, we denote this with the variable r and theta. Now the directions go something like this. Let's start at the origin, facing the positive x-axis. Then we turn counterclockwise theta radians. And we walk forward r units in the direction we're facing. Really, all we're doing here is specifying the direction to walk with theta and the distance to walk with r. To make this concrete, let's try to plot the following points in polar coordinates. First, consider the point 2 pi over 4. Our directions tell us to start at the origin facing the positive x-axis, and we turn counterclockwise pi over 4 radians, and so we're facing this direction. Then we walk out 2 units, and the point we land on is the point 2 pi over 4. Next, let's do the same thing with the point 3 minus pi over 4. This will work the same way, except negative angles mean we turn clockwise instead of counterclockwise. So we're facing this direction, and then we walk out 3 units. Finally, consider the point 7 pi over 4. We turn an angle of 7 pi over 4, and so we're facing this direction, and we walk out 3 units. Notice that we landed at exactly the same point as in the last example. Therefore, we see that a point may have multiple representations in polar coordinates. In other words, the polar representation is not unique. We just saw one example demonstrating this, but it's not too hard to generalize this example. In particular, the point r theta is always going to be the same as the point r theta plus pi over 2. Another place we see a lot of non-uniqueness is at the origin. In particular, anytime r is equal to 0, we just stay at the origin. So any point of the form 0 theta will represent the origin. Next, we'll introduce another form of non-uniqueness by allowing for negative r values. In terms of our directions of polar coordinates, we'll think about negative r values as turning around and walking in the opposite direction. In other words, the point negative r theta is the same as the point r, theta plus pi. For example, consider the point negative 3 pi over 4. Our directions tell us to turn counterclockwise 3 pi over 4 radians. So we're facing this direction. But since r is negative, we turn around pi radians and walk out 3 units. Alright, so now we have these 2 different ways to represent points in the plane. But how do we go between them? First, let's talk about how to go from polar coordinates to Cartesian coordinates. It's going to be helpful to draw a picture. Say we're given a point r theta in polar coordinates. Those coordinates represent these measurements. Now, we can also draw our Cartesian coordinates in this picture. They represent these measurements. Now the goal is to get the blue measurements from the pink ones. To do this, notice that what we've drawn is a right triangle. So we can use what we know from trigonometry to help us out. Let's start with x. How are we going to write x as a function of r and theta? Well, notice that x, r, and theta form the angle, adjacent side, and hypotenuse of this triangle. Therefore, they are related by the cosine function. In particular, x is equal to r times cosine of theta. If we do the same thing for y, we find that y equals r times sine of theta. Let's go ahead and do a couple quick examples. Say we're given the points 2 pi over 4 and 3 negative pi over 3 in polar coordinates. To write these in Cartesian coordinates, we just plug in the r and theta coordinates into the equations we just found, and we get that these are the points square root 2, and 3 halves minus 3 square root 2 over 2 in Cartesian coordinates. All right, now let's try to go the other way, from Cartesian coordinates to polar coordinates. Again, we draw the same picture, and now our goal is to find the pink values given the blue ones. Let's start with r. We want to find r given x and y. However, notice that these are all the sides of the right triangle. Therefore, they are related by the Pythagorean theorem. And we get that r squared is equal to x squared plus y squared. Next, let's deal with theta. We see that theta, x, and y form the angle, adjacent side, and opposite side of the triangle, and therefore they are related by the tangent function. And we find that tangent of theta is equal to y over x. All right, so now we have equations to retrieve polar coordinates from Cartesian coordinates. But there's actually a little ambiguity in how to apply them. For example, say we have the point 2, 2 in Cartesian coordinates, and we want to write this in polar coordinates. We can start by plugging in these values into the r equation and find that r squared equals 8, which implies that r is equal to plus or minus 2 root 2. Next, we plug in our values into the theta equation to find that tangent of theta is equal to 1. Now, notice that this equation has two solutions if we consider angles from 0 to 2 pi. The solutions are pi over 4 and 5 pi over 4. So, we have found two different r values and two different theta values, but will any pairing of these values work? It turns out the answer is no. The way we're going to find the right pairing is by identifying which quadrant we want to land in. Notice that the point 2, 2 is in the first quadrant. So, we need to make sure that our polar coordinates also land us in the first quadrant. If we pick the angle pi over 4, then we're actually facing into the first quadrant. So, we should pair it with a positive r value so that we walk into the first quadrant. Therefore, the point 2 square root of 2 comma pi over 4 is a good polar representation of this point. On the other hand, if we chose the angle 5 pi over 4, then we're facing into the third quadrant. So we should pair it with a negative r value so that we walk backwards into the first quadrant. Therefore, the point negative 2 root 2 comma 5 pi over 4 is also a polar representation of our point. Let's do the same thing with the Cartesian point 1 minus square root of 3. We start by plugging these values into our equations to find that r equals plus or minus 2, and theta is either 2 pi over 3 or 5 pi over 3. Again, we're restricting ourselves to angles from 0 to pi over 2. To find the right matching of these values, notice that 1 negative square root of 3 is in the fourth quadrant. The angle 2 pi over 3 is facing into the second quadrant. So we should pair it with a negative r value so that we back up into the fourth quadrant. And so we get the point negative 2 comma 2 pi over 3. On the other hand, the angle 5 pi over 3 is facing into the fourth quadrant. So we should pair it with a positive r value so that we walk into the fourth quadrant. And this gives us the point 2 comma 5 pi over 3. Before we move on, remember that there are infinitely many ways to represent each of these points in polar coordinates, and we only gave 2 for each. So if you're up for it, it might be a good exercise to try and find some others.